let's focus a little bit on gravity, mass, and weight. Mass is a measure of how much an object, that's the definition of physics, how much an object resists being accelerated. It is not weight, that's very important. But also mass is a measure of how much matter we have in the object. For example, if it is an amount of rice, how much rice do you have in it? If it is a person, how much matter is in that person. Now, the weight, we also call it force of gravity or gravitational force. It's going to depend on the mass of the object. The greater the mass of the object, the greater the pull that the Earth is going to exert on that object. This is like what we mentioned before. When in free fall, in the absence of air resistance, or in general in the absence of all forces except the gravitational force, the acceleration due to gravity is the same for all objects, irrelevant of their mass and shape. Now, the gravitational force or the weight, this is the definition for it. It's the mass times the gravitational field at that point. Again, we usually use F sub g to refer to it, and some people use W to say weight. Now, I said at the surface of a planet, if you are or a moon, for example, if you are at the surface of the moon, small g is not going to be 9.8 meters per second squared. It's going to be actually 1/6 of that. By the way, 9.8 meters per second squared downward. So it's going to be about 1/6 of that. If we are on Jupiter, it's going to be larger than that. On Mars, about the same value as that. Okay, now it's going to depend on where the mass is. Actually, even on Earth, we'll see in a little bit, it's going to depend on your location. The weight, for example, of something, if you measure the weight of something in Savannah, Georgia, that is at sea level, you are going to get a different reading than if you read the same value at, I don't know, but probably I can go as far away as Colorado, where it is way beyond sea level. Then the weight or the gravitational force on that same amount of mass is going to be different. Now, why do we have a gravitational force? This is the key thing. Excuse me. Whenever we have two masses of any type, look around you. The book around you is a mass. You are a mass. Look around you. There is another person next to you. That person is a mass. You are a mass. Any two masses. What's interesting, and the kids get a kick out of it when I tell them, all masses attract each other. All masses. Okay? The kids, the way they get a kick out of each other, I kind of, usually what I do, I take a guy and I say, look, these two guys are attracting each other. Of course, everyone else laughs. They don't like it very much, but that's true. Because both of them, they have a mass, they attract each other. To help their pride, usually if I'm talking with kids and stuff like that. And then I bring in a lady as well, and I say, both are attracted to her as well. But this is irrelevant of any other type of attraction. This attraction is due just to the mass. How big is this attraction? Actually, we can calculate it later on. It's not really that big. But as an expression, that's what it is given by. So if I'm taking as an example a blue mass and a red mass, the red mass is going to be attracted to the blue mass through this force. So the blue mass is exerting this force on the red mass. So the notation I'm using here, and I'm asking you to use in the second activity, force of the blue on the red. How much is it equal to? It is given by this formula here. A certain constant big G that's very tiny, which is 6.67 10 to the minus 11 Newton meter squared per kilogram square, very tiny constant, times the mass of the red one times the mass of the blue one over the distance separating them squared. The distance separating them, we measure it from center to center. So what does this equation tell us? It tells us the more massive the objects are, the more they are going to attract each other. It tells us the further apart they are, the lesser the attraction. And as I mentioned earlier, I focused on the force that the blue one exerts on the red one, but similarly, the red one is going to exert an equal force on the blue one, but that force is going to point in the opposite direction. It's going to make the blue one attracted to the red one. So that's why here we are writing force of the blue on the red is equal to the force of, actually, I'm glad I mentioned it, force of the red on the blue. Okay, they are supposed to be both different symbols. And it is equal to G, M red, M blue over D squared. I'm not sure how many years I used this slide. I never noticed that the symbols were written wrong. Okay? So that's a fundamental concept. This is what we call the law of universal gravitation. Now, actually, this is the law that Newton was most famous for, the law of universal gravitation, that says any two masses are going to attract through that force. What's even more, why do we call it universal? Because it deals with any two masses. Now, if we take one of you, for example, in the class, let's say I'm going to throw in a name of one of you, let's say Mandy here, as the red mass. Now, Mandy is going to be attracted to any mass in the universe. That's what that means. It means that Mandy is actually attracted to the moon. We can consider that blue mass as the moon. Mandy is also attracted to the Earth. Mandy is attracted to Mars. Mandy is attracted to the Sun. Mandy is attracted to the building at Kennesaw. Mandy is attracted to her book. Mandy is attracted to the computer screen. Mandy is attracted to all galaxies in the universe. She's attracted to a lot of things. That's why we call it universal. Okay? Now, this is really what we call the gravitational force. This is really the origin of the gravitational force. What we've been using before as here, writing Fg is equal to mg, is a special case of that. What kind of a special case is it? It's the force that Mandy is going to feel because Mandy is attracted to the Earth. It is the special case where we are discussing the gravitational attraction between various objects at the surface of the Earth and the Earth as a whole. That's what makes this special. Okay. I'll stop here, and I will try to address this in a little bit more detail in the next recording.